So today, mostly, we will discuss parabolic equation in polar coordinates. Should I start? Thank you for coming. That's seventh lecture of our diffraction course. I hope you enjoyed previous 6. But unfortunately, I need to tell you something. Last time I was not exactly precise, and maybe to put it more frankly, I lied a bit. So some of the things were wrong. And thanks to Alice who attempted to do the homework, I noticed it. So first I will comment on the problem of diffraction of half plane. I will write down the correct solution. I kind of mentioned it, but I didn't do it for some reason. So we start from the comment on parabolic equation in Cartesian coordinates, and then we will proceed to parabolic equation in polar coordinates and the problem of diffraction by symmetry. So we did everything good for perpendicular half plane, but made some mistakes with parallel half plane. And indeed, with this problem, we should be a bit more careful than I was last time. So, what was the geometry? This is our half plane. We want the Dirichlet boundary condition satisfied on the surface. And we have this in way. Is amplitude 1 falling into this point. And we want to find the scattered field somewhere on the right side. Didn't write the parabolic equation. Tom, did you had a look on the lecture?
Yeah, a brief look.
So you're more or less aware what's happening?
I think so, yeah.
Yeah.
I'll ask if I...
Can somebody remind me the equation, the parabolic equation? Write it down. So it's g2 gx squared plus something but not x, y. Equal to 0. Is this right? Yes? I don't remember.
How come there's no x squared soon?
Yeah, we discarded the square term. Apart from the x square term, here we have plus. And for u, we have u in plus u scattered, and u in for our case is just 1. And as we said, this equation only supports wave going from left to right, and we want to find our wave field somewhere here. And okay. And last time I proposed to use propagator formula, which is also I didn't write in the lecture notes today, but I think it's something like this. So we want suppose it like this. Yeah? Good. Something like this. And what's the problem with this formula? So it's hard to apply this formula straight away because we have a boundary in horizontal line. And I last time I said, okay, the problem is symmetric, we will only apply it in half space. It works. It's more or less a good approach, but then we need to symmetrize our field back that the boundary condition will be satisfied. And I just wrote down part of the field which definitely doesn't satisfy boundary condition on the half line. And now I will follow a more formal approach where I can apply this formula straight away without any tricks. So correct solution. We first, similarly as we did for Newton's equation, we start from method of reflections. I just wanted to skip this part last time, but it seems this part shouldn't be skipped. So now I say, okay, let's reflect our half line, and we have two sheets. Sheet 1 and sheet 2. And so we reflected the space, also we reflect the incident field. So on sheet 1, it's a physical sheet. We have our wave with amplitude 1. Since it just goes along the x-axis, we will have the similar wave on sheet 2, but with amplitude -1. And then I do, as we say in Russia, horse move. You know, when you play chess, you have a horse. Horse can jump across other figures. I can deform this cut. I don't like this cut this way because I want to use this formula and I want to integrate from minus infinity to plus infinity. But of course, once I have this picture, I can deform my cut any way I want. It doesn't affect anything. It doesn't matter. And so on step B, deform the cut. I redraw the same picture. But now I just deform cut and for clarity draws in the same wave. And having this geometry, it's quite easy for me to apply this propagator formula because now I know the field on this line and my solution is my solution is field on this node somewhere. Line x equal to n. That's where I want to find it. But of course in the upper half plane, but after symmetrization it will not matter. And so, but I know field everywhere starting. So here the field is just, let me use, so it's just one, and then this field, it goes actually here, because it goes through a cut on the other sheet. So starting field here is -1. And that's it. So I will get a similar formula to what I had last time, but last time I only had this term and didn't have this term, and it definitely comes from the symmetrization. It's more or less the same, but reflected. And using this formula, we can write down the solution. This is from this part. Then similar thing. Comes from this part. At least -7. So definitely when y is 0, it's 0. So we satisfied the Dirichlet boundary condition, and because of this structure, it's by construction a solution to parabolic equation. So we have everything right. We also should have in mind some radiation condition, but since all our ways go from left to right, our solution is physical. And okay, for this one, I repeat this expression so you can compare it with a textbook. What's the name for this?
Rubber eraser.
Eraser. Okay. It's no problem. Eraser. Thank you. So I erase this and this is equal to this. So I will write down it in terms of Fresnel integral. that with different labels. This is a correct solution, at least I hope. You can compare it with exact solution to Green-Coult's equation, and it will be close for small angles. So, sorry for giving misleading or real information last. I hope I fixed the issue. Do you have any questions? Was it clear? So that's probably should answer one of your questions, Alice.
Yes, thank you.
Okay. Let's forget about this thing forever. Now go to the main topic of our lecture, which is pretty exciting. So we will study a problem of diffraction by a cylinder, which was solved, like this problem can be solved exactly for Green-Coult's equation if you use just separation of variables. But the solution will be series, and this series doesn't always converge well, especially when you have a high frequency wave. This problem was solved by Fock. Fock using parabolic equation, I don't know, maybe 100 years ago, maybe at least a bit less, 70 something years ago, and it had a clear practical application. So it was solved for the description of propagation of radio waves along the surface of Earth, which was important for radio communications back in the day. What he found, that, okay, we'll draw a picture, that some diffracted wave can propagate for quite a long time. So when we send a plane wave on Earth's surface, like a long radio wave, then this wave will creep along the surface for like, and it can make a full turn and maybe several full turns, which is quite nice feature to have. And that was not easier to understand from a mathematical point of view. I will probably not go into all these details today, but I will just describe his method and give you a formal solution. So, point 2 of our lecture is diffraction by cylinder. Of course, we have some paraxial wave propagation. So we have a cylinder. And of course, I suppose that radius is quite big. Then I have a plane wave coming like this. And I will use some non-conventional coordinate system. So this is the radius of the cylinder, and I have a polar coordinate r. I have polar angle phi, and I want again the boundary condition be satisfied on surface of cylinder, but I want to use curved coordinates. With some other chalk, which follow, one of them will be L, which follows the surface of the cylinder, and another one will be H, and Parabolic L is R phi, okay, and H is R minus R, so this is difference H. Okay, and again we start from, so I won't be using parabolic equation in Cartesian coordinates as I said, because I want to make use of the symmetry. Now I have cylindrical symmetry and I have paraxial propagation. That's how I suppose my waves should behave. Of course, to prove it, I need to do some additional work, but we will skip it. We will get the solution, and like somebody then can show that this solution is close to the solution of the exact problem. And but anyway, formally we again start from Lincoln's equation. I have tilde, so then I can reduce parabolic variable. And okay, I want one of a priori estimates that I have is that Kr is much bigger than 1. So I have short waves going along slightly curved surface. That makes sense. So if my surface is kinda, if it's almost flat, I can expect that the diffraction will mostly happen on small angles. So my parabolic approximation will work. And then I will use the following results. So this is my new variables in MH, and what I do, I suppose that all the rapid wave oscillation happens along the surface of the cylinder, and it definitely should work for very big R. Okay, R, I want to be dimensionless. So, okay, let's repeat the procedure from the previous lecture, but now for this substitution. So first, let's do change of variables for Greenwald's equation. Just rewrite this equation in new coordinate system. Okay. So I did it, and here is the result. And I hope you know how to change variables in the partial differential equation. So that shouldn't be a problem for you. Anyway. So it more or less has the same form as Gregori's equation in polar coordinates. I just use this notation. That's it. So of course, I suppose the first thing I will discard the everything that R is much bigger than H, where H is, like as I said last time, it's a scale for amplitude variation along radius. So I kind of suppose that all the diffraction, all the like complicated diffracted field will live somewhere around the surface of the cylinder. And if I go far away, I will just have a plane wave propagated straightforwardly, almost unaffected. So R is very big. First I will discard this term, but that's not the only one. Second, I will play with this one using that R is big. So I have that's how I approximate this term. Let's rewrite this. Taking this stuff into account, we have then we use this substitution and rewrite our equation once again for new variable u. Sorry for this body algebra. Please don't fall asleep. I was thinking whether I should skip this part completely. But I'm afraid if I skip it completely, you will stop following. So this bit comes from differentiation of this bit. What else do we have? We have something from differentiation of this bit, also k-squared term. And then some cross terms. Because here we differentiate twice. Once we differentiate the exponent, another time we differentiate the field. And there will be first order terms as we had last time. This is the second order term, and then cross terms. this thing produce 3 terms and this thing produce 3 terms. When we differentiate for the first one we have 2 terms, then another 2 terms, but one of them will go, so we have double here. And okay, let's discard something. Of course, you know, in the spirit of parabolic approximation, you expect only waves to go along the surface, so there should almost not be any backscattering in this case. And I will get rid of all second derivative on L, on the lateral variable. So this thing I don't want to be a part of my equation. But then also I will get rid of this term because R is big and H is small. And this term I will preserve. And this term just cancels, these 2 terms cancel each other. And so what do we have here? And to make this thing formal, more formal, I had the following, so I kind of used the following estimates, that k minus 1 is much less than h, which is much less than L. And here H and L are some characteristic scales in lateral and perpendicular direction to the surface of the cylinder. Put the 60 minutes here. So, what do we have then? Yeah, just check. Okay, we definitely have a parabolic equation, but now we have some curvature related term. And the next step I will do, just to make things a bit more neat, I will introduce dimensionless variable. So we have quite a few parameters, h and k. So it's 3 parameters. When you have more than 1 parameter, the first thing you should do is to make your equation dimensionless. And here it's very useful. So I will write down the the way I did it, it might look a bit unclear, but of course you can just solve this equation the way it is, and then you will see how it should be dimensionalized. And then you will have very neat equation. So, what conclusion can we make from this one? One important thing that once we solve this equation for one pair of K and R, then we know solution for all pairs of K and R. So we kind of solve it once, and then we know solution for all cylinders, for all wavelengths. However you want to call it, but for all KRs. We just keep okay, we have this equation, and then we follow the algorithms we developed during previous lectures. So it's just step 1, step 2, step 3. First we need to understand the structure of plane wave for this equation. What is a plane wave? So let's have go resurface once again. Let's introduce Cartesian coordinates for a while, for a very short period of time, just to be able to convert from usual plane wave for this plane wave in the coordinates R and H. And so for the inverse equation, U in, since it's plane wave going, so I'm studying only one plane wave today, the one propagating along x-axis. This is just in kx. So this is kx. So for parabolic, we take this wave, but we subtract the oscillatory term with L. And let's do some approximations as we did last time. So, what so here I used polar coordinates and our definition for H. This thing we call, as you remember, this bit is L. So I just used our definition for L. Then so I suppose that phi is small, angle of observation is small, and I use the following. Nobody knows the second term for the Taylor series of sine, so I googled it. And okay, substituting this bit will cancel. And I will have, and also in dimensionless coordinates, it will look like this. And then, of course, we did some approximations. This is like we wrote down an asymptotic expression for plane wave. But the next thing we do is we take this expression, substitute it here, and this thing will be an exact solution of parabolic equation. So it's an approximate solution of Green-Gold's equation, but exact solution to this equation. Got like we're lucky that after some approximations we got the solution. That the solution stayed exact. Of course, there is a formal way to prove, to see it why it happens. But it doesn't matter. For practical things, that's what we do, then we check, and it always works. Okay, let's make a short technical break.